Okay, so first of all, thank you to the organizers. I mean, it's a pleasure to be here. This is my first visit to ICTS. I hope you can hear me at the back. It's a nice campus, and I think it's good to be here. So in fact, Subrabhati made my life easier. So I mean, a lot of things that I wanted to say are already included, I mean, in our talk. But I'm going to focus more on the DUNE part, and then I think, in that sense, where India stands and Indian institutions stands on the DUNE participation. I think that's something that I'm going to talk about. Okay, so so we already know, we already know about the neutrinos and then their antineutrinos, and we also know that they interact only by the weak force, and that's because I'm an experimentalist. So understanding the interaction is important because that is how we're going to detect them. And in the standard model, we also know that these neutrinos are a massless particle and they are left-handed particle, and the antineutrinos are the right-handed particle. So they are, the interaction cross-section is very small, but they are really in abundance. For example, we are emitting about 340 million neutrinos per day, and we are getting about 100,000 billions of neutrinos from the sun coming to us. And in our entire lifetime, we'll be stopping only maybe in one of them. Otherwise, it would have become a good neutrino detector. All right. So as an experimentalist now, when we talk about this interaction, if I have a new mu charge or interaction interacting with a detector, so I'll be mostly looking at a muon particle, which is going to be a longest track, that decays to emission electron at the end of the process. And then if we're talking about a new charge or interaction, so I'm going to look for an electron track there in a detector. But just because electron goes through this multiple scattering as well as Bremsstrahlung processes, so it's not going to be a track like the muon track that we're going to see. So similar to that, if you're talking about the neutral current interactions, I'm going to mostly looking at the production of the hadrons because of the neutral current interaction in the detector material. Now, just because, again, to put things in perspective, just because you're talking about a weak interaction, so this 3 MeV neutrinos that you produce in the fusion reaction from the sun, so that's going to travel about 53 light years for water on average before interacting. And this is, again, to put things in perspective, then if you take a same 3 MeV positron produced in the same fusion reaction, it's going to travel only about 3 centimeters on an average, okay? So that is how the low interaction cross-section that we are talking about right now. So in terms of the absolute measurement of the cross-section, it's about 10 to the power minus 38. That's the order of 10 to the minus 38 centimeters per nucleon at around 1 GeV. That's the smallness of the interaction cross-section that we are talking here. So a good thing is that we have a lot of sources for the neutrinos. I think we have seen that in many slides in the last 2 days. So including the atmospheric neutrinos, the solar neutrinos, the reactor ones, and of course, you're getting neutrinos from the supernova and of course from the man-made facilities as well, like the reactors and the accelerators. So they have a wide spectrum. For the solar, we are getting neutrinos in a range of around MeV scale. The man-made one, whether it is a reactor or the accelerator, so we are getting in the range of MeV to GeV range, whereas for the atmospheric one, you're getting neutrinos in a range of MeV to TeV scale roughly. Okay, but I think of course the flux is falling very rapidly there. Now, in the standard model, this is something that we already talked about, that they interact only via the weak force, and the neutrino flavor is strictly conserved. That's what we have known from the standard model picture. And then, of course, they have no mass. But then when at least I started working for my PhD, this is something that was established by the experiment at the time that the neutrinos oscillate from one flavor to another flavor. And that is something that indicates that the neutrinos are actually not massless particles, they have certain mass. And then we have also learned in the process that the neutrino mass states are different from the flavor eigenstate. And as they travel, so they actually change flavor from one type to another type. And this is basically a first signature for the some physics that is BSM that we're looking for. Now, neutrinos mix just like the quarks. And I think that is, I thought of putting this picture together because that is something that was pointed out in the previous talk. So here in this case, in case of neutrino mixing, we have the PMNS matrix to talk about the relationship between the mass eigenstate and the flavor eigenstate. This is similar to whatever we have learned from the quark sector, where you have a CKM matrix. But I think there's a vast difference between the two. And I think that is something that we need to understand why it is so. For the CKM, we see that these matrix elements are pretty diagonal. They are of the same magnitude, similar to the off-diagonal elements. Whereas for the PMNS matrix, we don't see a particular pattern in terms of the magnitude. And I mean, there's no definite pattern is evolving from the measurement that we have been doing so far. And I think that is something maybe, I don't know whether there is something that we can draw from, but this is certainly some puzzle there. We have done pretty good in the last 20 years to measure these matrix elements. Of course, this is parameterization of the same PMNS matrix in terms of the angles and then the delta CP phase here. This is, I'm again talking about the three-flavor Neutrino oscillation. And then many of these quantities can be measured from the long baseline accelerator experiments like the DUNE or the NOVA that is running right now. And in fact, this is the best fit result for this matrix element. This was being done by the new fit group in 2021. So these are the best fit result with both the SK atmospheric data as well as without the atmospheric data from the superconductor experiment. Okay, so these quantities are pretty nicely measured, but I think, of course, you can do better than this precision that is listed in this particular slide. Now, when you talk about, again, a three-flavor Neutrino oscillation, so as an experimentalist, again, if we are looking at a certain neutrino flavor, the probability to observe a certain neutrino flavor, so that depends on the mixing angles and also the mass square differences between the neutrino masses. So this is, I mean, if we write down this equation for the three-flavor neutrino oscillation, this is something that we'll be writing, where the probability depends on the mixing angles as well as the mass square differences. Now, as I said earlier, so many of these matrix elements are pretty precisely measured at this time. For example, for θ23, the preferred value, the best fit value is around 49. And if you look at the precision here, it is actually pretty good at this time, I mean, compared to whatever we have been doing in the quark sector. So they are pretty precisely measured already in about 20 years of time, but I think, of course, we need to do better than this, and that is what the effort is. The delta M squared T2, again, this is again is measured pretty precisely. And similar to that, delta M squared to 1 is also being pretty precisely measured. What is not known at this time is delta CP value. I mean, that is something which is unknown. We have some favored number, but again, or disfavored number, but then again, we do not know what this delta CP is. And we also have some bound on the sum of the neutrino masses, which is mostly coming from the cosmological observation at this time. It is coming out to around 10 to the minus 6 times of the mass of the electron. And that is something that is has to be measured in experimental program, not the oscillation one, but something else. I'm going to talk about that. So what we're looking at is delta CP right now for an experiment like DUNE. And if the delta CP is not going to be 0, that is going to lead us to this particular measurement where the nu alpha going to nu beta, for example, the probability of that is not going to be the same as the nu alpha bar going to nu alpha beta. And therefore, if I'm going to calculate the CP violating parameters, so that is how I'm going to do it, including multiplying the sine and cosine of the various angles, including the delta CP. And that's because all these angles are non-zero. So if the delta CP is non-zero, of course, then I'm going to conclude that there is some kind of CP violation in the case of the neutrinos as well. Okay, that is something of our interest. So of course, again, I think this is a big question that we're trying to understand, that why the universe is mostly matter, not the antimatter. And of course, one of the possible answers is CP violation. And we have seen CP violation in the quark sector that all of us know. And of course, then that is not sufficient to talk about all the matter dominance in the universe. And then, of course, you need to look for CP violation elsewhere. And that is where the CP violation measurement in the lepton sector is going to play a very important role. And therefore, measurement of delta CP is critical at this time. All right, and the other, the second known unknowns, I think we heard about that already. I mean, again, we have only been able to measure the mass square differences between two different neutrinos, but we do not know which ordering is the preferred one. For example, whether it is a two light states and then one heavier state, or it is the inverse of the particular diagram, where the two lighters, I mean, to nu1 and nu2 are at higher masses compared to the nu3. So this normal hierarchy or the inverted hierarchy, which one is correct picture for the neutrinos, I mean, that is something it is still unknown, and that is something that we need to find out. Okay. Neutrino mass is again is not known at this time. So we have cosmological observation that is putting a limit at around 0.12. electron volt at 95% confidence level. But this limit relies heavily on the cosmological assumptions, which are that goes that goes into this calculation of this limit. Then similar to that, we have this Neutrinos double beta decay experiment, where we are putting limit in this particular range right now. But again, that depends on the nuclear matrix element, and also on the assumption that they're the kind of Mariner particle, not the Dirac particle. Okay, so there are limitations on this particular two process. Then if you go to to find out the beta decay spectrum endpoint, that is putting us some important limit at this time. And of course, and the best result has come recently, which is putting the limit at around 0.8 electron volt from this particular experiment. And here again, improvement in the technology is going to play a very important role to find out where the endpoint is for the beta decay spectrum. Okay, that is where I believe some important results is going to come forward in the future. Okay, now let's talk about the DUNE. So this is going to be a facility where we are going to get a muon neutrinos, also the antineutrinos from a high power proton beam. So we are getting about 1.2 megawatt of beam from day one, and this is going to be upgradable to 2.4 megawatt. And then we are putting massive liquid argon TPC as a Far detector in South Dakota, which is going to be around 1.5 kilometer deep underground. So there will be 4 modules here, including that is going to give us about 70 kiloton of liquid argon detector. And then we are having a near detector complex with multiple detectors. So this is going to be located approximately 575 meter from the neutrino source at Fermilab. And this is going to help us to understand various neutrino interaction with the target material that we are interested in understanding. Okay, so this is basically a cartoon of the facility where this is the Far detector site. And this is the near detector complex, where there are 3 different detector concepts that we are working on. And this concept is already being accepted by the collaboration. I'm going to talk more about that. And then, of course, the beamline is going to provide the necessary beam for us to look at about the cross-sectional measurement, the flux measurement, as well as the oscillation probability for the nu oscillating to the nu E or the disappearance mode. Okay, so this is again a very large collaboration, and India is playing a very important role here in this particular collaboration. And we have about 35 people from India at this time working on the DUNE collaboration. And of course, there are more scope to expand. And if you're interested, you can, of course, speak to me after this talk. So the Far detector, so this is again, as I said earlier, so this is going to be underground, about 1.5 kilometer deep underground at South Dakota site. This facility is already hosting a lot of other particle physics experiments. And so this excavation of the site has already started. That requires removal of about 875,000 tons of rock. And that process has already started. And in the phase 1 of this particular Far detector program, so we're going to put 2 17 kiloton detectors. So each of this module is going to be about 18 meter by 19 meter by 66 meter. And so in the phase 1, so the 2 modules will be put in there. So this one and this one, or this one and this one. And the one is going to be of horizontal drift. This is going to be based on a model from the IISc as well as the microbone detector. And then the other module is going to have the vertical drift, which is basically a new method or technology that has evolved from the dual phase design, where we have just built a prototype at CERN. And then the other 2 modules are still, the technology for that are still undecided. We just had a workshop in Europe to find out what should be the technology for the other 2 modules. And again, I think if you have idea, I think that's something that the collaboration is going to accept and then look into that. So why we're using liquid argon? So argon actually scintillates. It produces about 20,000 photons per MeV at this particular 500 volt per centimeter. And argon can also be easily ionized. So then you get about 55,000 electrons per centimeter. So what you can do, you can in fact use both this particular 2 information, the ionization as well as the scintillating light, to do a kind of 3D event reconstruction. And that's a very important point here. So what do we do? So when the neutrinos interact with the argon, it produces a charged particle, and argon also scintillates. So light is being detected by the photon detectors that we put on the detector. And this charged particle that ionizes the gas, the argon gas, the electrons drift slowly to the anode. and that signal is being collected by the readout wires. And combining the signal from the photon interaction or the photon production in the detector with this ionization signal, you can do a 3D event reconstruction. Okay, that's the beauty of this particular technology. So this provides this nice 3D imaging, and we get about few millimeter resolution over this large volume that we are talking about. And it's also a fully active detector. That means it is actually acting as a fully active calorimeter, and that allows you to do the particle ID by DDDX measurement, the range, and an event topology. Okay, so that's an important point to look at the various interactions that we're interested in. And it's also it's an excellent detector technology as well for different energy scale. I mean, both at the high energy as well as the low energy. When I'm talking about the low energy, I mean about 10 MeV here. There are, of course, challenges here because this technology is not being proven at this large scale. We are talking about 17 kiloton. So we have built detector of the range around a ton now. So I mean, that technology has to be proven at this very high for that large volume. Okay, that is where the challenges are. Okay. So as I said earlier, so there will be two modules for the Far detector. So there's a horizontal drift module, which is going to be a 3.6 meter horizontal drift. The arrangement is going to be like this with an anode, cathode, and cathode and anode geometry. And then the charge readout is going to be done with the wires. And of course, we're going to place the photon detectors on the anode plane so that we collect the signal from the scintillating light as well. There's other module that I talked about is going to have the vertical drift module, and it has evolved from the dual phase design. And in this case, the drift is going to be about 6.5 meter in this vertical direction. And the geometry in this case is going to be putting an anode plane followed by a cathode and anode geometry. And again, this is in this case, the charge readout is going to be done by the printed circuit boards. And then we are going to put the photon detectors on the cathode plane. Okay, so this is a picture of how this thing is progressing at the South Dakota site. So this rock removal process is ongoing at this time. Hopefully, I think this facility is going to be ready to put the Far detector in the near future or very soon. Okay, so this is about the beamline. So now there's a PEEP2. I mean, we heard about that talk, and India is participating in this particular program very heavily. And this upgrade of the PEEP2 facilities to deliver this high-powered beam to about 1.2 megawatt to LBNF in this particular energy range, 60 to 120 ZeV. And that is going to be upgradable to 2.4 megawatt in the phase 2. And this upgrade process, I mean, that the scope of this upgrade involve the including, making this 800 MeV superconducting Linoc. There are a lot of modifications to the booster, the recycler, and also the main injector. And India, it's a broad international program, and India is deeply involved. I mean, we have seen this involvement in the talk today and this morning before lunch. Okay, and this particular facility is going to give us both the neutrino and the anti-neutrino beam, and in this particular energy range, roughly 0 to 8 GeV. So therefore, the neutrino spectrum, this Far detector is going to see some kind of broad spectrum, and that is going to help us look at both the neutrino, the first and second oscillation maximum. Okay, so then there's a near detector concept that has evolved over time, and that is something that is closer to my heart. At least that is something that I worked on very closely. And in this case, the goal of this near detector is to constrain the systematic uncertainties, which is required for the oscillation analysis. Now, I mean, we are already talking about the precision measurement of the neutrino oscillation. So therefore, the constraining the systematic uncertainties because of either in the flux measurement or the cross-section measurement is going to play a very important role. And that is something that we need to control to do the precision measurement in the neutrino sector. So here in this particular ND complex, we're going to have the ND hall, which is going to be located about 574 meters from the target, and it's going to be underground by about 60 meters deep underground. It's not deep. And in the phase 1 of the complex, we are going to put this highly segmented liquid argon TPC. That's going to provide the same target as a Far detector, and then that is basically this block here. And then there's a temporary muon spectrometer, which is going to follow the liquid argon TPC, which is shown here in this small block diagram. And that is going to be upgradable to ND-GAR, the gas argon TPC, in the phase 2 of the program as of now. That's the plan. And then there's a system for on-axis neutrino detection, which is going to remain on-axis throughout the running of the experiment. Whereas this combination of these two detectors are going to move in about 30 meters in that particular direction, so that you can scan the neutrino energy spectrum. Whereas this detector is going to remain on axis throughout the running of the experiment. That is going to help us to do the beam monitoring as well as various cross-section measurements that we want to do. Okay, so this capability to move this part of the near detector complex, these two detector, to the off-axis direction, is basically what is called a DUNE prism concept. And so therefore, here in this case, so as I said earlier, it's going to be moved by about 30 meters, so that you can look at the various energy spectrum. I mean, we can scan the energy spectrum by moving this complex, these two detector in that particular direction by about 30 meters. Okay, so that the spectrum can be measured or a scan, and that is going to help us to look at the Far Detector spectrum and understand it in a better way. That is going to help us to reduce the uncertainties on the calculation that we can do. Okay, so there's a status of the prototype. So DUNE prototypes are already being built at CERN, and these are being tested with the charged particle beam. So in fact, we have already built to 1 kiloton cryostats, and these are being used to validate the Far Detector components at a full scale. Remember, we have to build them 17 times larger than whatever we have been doing so far. And we had a successful run in this particular duration, 2018 to 2020. And then the next phase of this particular program is starting in spring of 2023. And that's basically the prototype which is being built at CERN. And there's already a physics result that has come out recently in 2020 based on this particular program. On the near detector side, I mean, for the liquid argons, this argon Q2x2 and the large detector has been built to demonstrate the capability of the near detector program, and then there will be 4 independent modules which are going to go to the beamline anytime soon. I mean, for understanding this particular concept for the near detector complex. The other one, for the sand, we are putting this STT prototype, STT tracking detector inside the magnet, the Chloe magnet. The detector is pretty much already ready. There's a magnet and a calorimeter which is going to move from Italy. And then inside that Chloe detector or the magnet, we're going to put this STT detector as a tracker. So there's already a prototype being built at JNIR, and that is that India is participating very actively. There's a student from IIT Guwahati working on that particular prototype design at this time. Let's look at the science program quickly. So basically, we are looking at the measurement of the lepton CP violation as a priority 1 program. And of course, we also need to resolve this mass ordering issue, whether this ordering is correct or this ordering is correct. I mean, that's something that we have to do quickly. And of course, then we'll be doing a lot of precision oscillation physics, including the parameter measurements, then a lot of other physics that can be done that we heard already from the previous speaker. I need to highlight the fact just because the detector is going to be very sensitive to the electron type of neutrino. So therefore, we should be able to look at the supernova burst as well and do a lot of astrophysics as well. For example, we should be able to detect about 3,000 new events in about 10 seconds from supernova at 10 kpc. Okay, so that's how the sensitivity detector is going to be. And then, of course, there are a lot of other nucleon decays and many other basic physics that can be done, including many other systematic or the cross-section measurement that can be done with the near detector facility that we are going to build. Yeah, I'm almost there. Okay, so what is the strategy? So here in this case, we're going to look at the nu E appearance probability that depends on θ1, 3, 2, 3, and delta CP, and also the matter effects. And all these 4 can be measured in a single experiment. I mean, it's going to help us to reduce a lot of uncertainties in the measurement. And just because it's going to give us a wide band beam, the beam line, and therefore we should be able to look at the first and second oscillation maximum together to understand this particular oscillatory behavior of the neutrino oscillation. So here is some results. I mean, this is again based on the simulation that we have done. So here we are looking at the nu E and nu E bar appearance. I mean, for the electron mode. and new mu to new E appearance. And here we're looking at a new mu disappearance for both neutrino and antineutrino. So in about 7 years of running, should be able to detect 1,000 of new E and new U bar interaction in the liquid argon TPC. And for the new mu and new mu bar disappearance, we should be able to detect about 10,000 of those events in about 7 years of time. And we're going to do the simultaneous fit to this particular force vector to look at various oscillation parameters. I mean, that's what the plan is right now. Okay. Looking at the CP violations sensitivity, I mean, we should be able to do this 5 sigma discovery for the CP violation in about 50% of the delta CP values. That is what's shown here. These plots are being made for different exposure, starting with 336 kiloton megawatt years, going all the way to 624 kiloton megawatt years. But I think for most of the time, I mean, for about 50% of delta CP values, you should be able to do a 5 sigma measurement there. And the resolution that we should be expecting in the range of 7 to 16 degree for the delta CP. And of course, we're going to rely only on the external input from the solar parameters for this measurement. Okay. So therefore, we should be able to do the simultaneous measurement on neutrino mixing angles and the delta CP in DUNE. On the mass hierarchy, again, we should be able to do this mass hierarchy determination for for about more than 5 sigma for all parameter values. That is what is shown here with these exposures. But then there is some recent work that has been demonstrated that with even with low exposure, I mean, with 66 kiloton megawatt year, the probability to extract the wrong ordering is very small. It's about 0.01. So with about 1.2 megawatt of beam running, we should be able to resolve this mass ordering issue in about 1 to 2 years of running of this experimental program. Okay, then of course, there's a lot of BSM physics that can be done. I think Subravati covered it nicely, so I'm not going to skip it. But this is basically the sensitivity we are going to get on the sterile neutrino, including the near detector information as well as the far detector information in this particular analysis. That's going to be very good there. Okay. Now, coming to the Indian program, I mean, I thought of putting it there because there's something that the Indian group has been working on from the very beginning since 2012. And then we actually initially proposed a detector that was based on the STT tracker, surrounded by a plastic scintillator-based ECAL and an RPC-based muon detector, and putting inside a dipole magnet. That design remained a reference design for the DUNE till almost 2018. And we have written the CDR that went to the DOE review as well. But then during this time, so there was a design effort to look at or to optimize the design of the detector near detector complex, because we thought of including some kind of hybrid detector concept so that there's a modular liquid argon TPC followed by a magnetized low density tracker. And that design activity evolved into the current final design that we have mentioned, that I mentioned in about a year ago from now. But that design that is finally accepted by the collaboration included the STT that we wanted to build back in 2012. Okay, so then from the political side, I mean, there's an agreement is being signed between the DE and DOE to support this collaboration with Formula on the near detector. And there's a monetary values also being added to it. But then there was a project implementation committee was set up in 2021 last year. And we were asked to submit a proposal to this committee that we have done in January of this year. And of course, we're still waiting for a decision from the DA and DST on that. And the DUNE collaboration is relying heavily on India for the STT success. And I think that's something that we need to keep in mind at this time. Okay, so that's all I had. And of course, this summary, I mean, the timeline is important. So the Far Detector is going to be ready by 2028. I mean, that is when the science is going to start. The near detector complex is going to be ready by the end of this decade. And then the full science of the DUNE experimental program is going to start from 2031 roughly, so that we have about 8 to 9 years to put things together. Okay, so that's my last slide. I'm not going to read it because I do not have time. But I think I need to point out this particular point that India is playing a very major role in the PIP2 upgrade program at Fermilab. I think it is important for India to reap the benefit by actively participating in the DUNE science program at this time. I think that's something that I like to highlight. Thank you for your attention.
Thank you, Bipul, for this excellent overview of the DUNE status and Indian participation. Open for question, comments, if there is any.
Yes.
I think you gave a number for supernova new events, right?
Yeah.
But does that include the coherent elastic? Most probably not.
I think not, I believe. Yes. That's
Any? Yeah. John.
So thanks very much for that very nice presentation. The one thing which I missed was right at the end when you're discussing the schedule.
Mhm.
So what is the reason for the delay to start taking data after the detector?
So, okay.
Apologize, I missed that.
Yeah, that's
Accelerator won't be ready.
so basically the Far Detector is going to be put in place by end of 2028. And that is when we are going to start a science program. I mean, we can do still atmospheric neutrino physics, for example. But the beamline and the other complex, the near detector complex, is going to be only ready by end of this particular decade. So 2030 roughly. So that the full science begin something like 2031 only. But we should be able to do all these other atmospheric neutrino physics by 2028.
And look for proton decay.
Yeah, of course we can do that. Yes.
Yeah. Why the delay?
Oh,
No,
that,
there is accelerator. He said that. People said. Yeah.
yeah, there's a cost overrun.
DOE delay the accelerator project.
Yeah.
So that's.
So
But it was actually from the beginning. It was there. There is a 1 year delay was there. Yeah. So so yeah. So that's what now becomes.
that's
2 to 3
right.
years.
Yeah.
Yeah.
Yeah. Hopefully, I think this is the final schedule. I mean, this was approved in July 2022. So hopefully, I think that will remain.
Any more comments, question? Okay. So let's thank people again.
Thank you.
for this talk.